Well, we'll go ahead and kick off. As a bonus year end, I have two tidbits today. First is that candy gummy worms contain more bones than actual worms, if you give that some thought. And secondly, a Christmas tree next to a burning fire is essentially forcing said tree to watch his friends burn. So the quaint little
Thank you for
Christmas
that,
scene.
Garrett.
What's that?
Thank you for that disturbing image. And I should say that every single one of us here should be burning propane in their fireplace. Come on, man.
Yeah, I will support that. So what is ResFrac? ResFrac is a fully coupled, fully integrated simulator that models the entire life cycle of an unconventional well in a single simulation. And the reason that we do so is in order to maximize the economic returns and optimize well design. So things like cluster and stage spacing, degree of limited entry, IOR, EOR, huff and puff, refracs, well spacing, etc. In order to do so in the most robust manner possible, we want to couple all of the physics that are occurring within a model or within that process. So that begins with hydraulic fracture propagation and tracking where proppant goes, then goes directly into those matrix fluids entering and flowing through the fractures into the wellbore, and finally any geomechanical impacts of pressure depletion happening in that rock matrix. And when we couple all of those things together, we get a holistic model where we can look at these effects and how a complex series of events interact with each other and produce the ultimate result, which is this production rate. So here I have 5 wells of 2 different generations, parent wells depleting, and then infilling with 3 children wells that are being simul-fracked right now. And then we can see all those wells come back online and that depletion happening. And so we can use this model framework to investigate and look at different solutions. So today we'll look at how we can set up different stage length simulations and assess the impact of stage length. But of course, there's any number of optimizations that you might do. Over the last 3 years, we've worked with 30 plus clients across the entire Western hemisphere. And that includes the Montney up in Calgary down through the Vaca Muerta in Argentina. We both license and consult, and it's that experience that we'll leverage today in talking about how we set up these sensitivities. Finally, February next year, we're kicking off this industry study on parent-child relationships. It's entering really the 11th hour if you would like to join the study, but feel free to reach out to me if so. Okay, so the topic today is setting up stage length or stage spacing. Wow, I really butchered that title. Setting up stage length sensitivities. So we'll go through the motivation, setup considerations, and ResFrac features and evaluation metrics. To begin, why should we care about stage length? And I have a paper over here from Peter Kaufman over at QEP that he wrote using ResFrac. And he actually looked at several design variables simultaneously, or presented 3 in the paper, but worked through these iteratively. You can see that stage length was varied as he went from design 1 to 2 to 3. And the objective there was to reduce well cost. So when we have a longer stage length, that means for a given lateral length, we have fewer stages, which corresponds to less time on location, which means ultimately a cheaper completion cost. So there's the benefit. The risk of a longer stage length is that you have a lower slurry velocity at the toe, all else equal. So if you have the same cluster spacing, that means you have more clusters, which means more fluids exiting the wellbore. And so at the toe, you have a lower velocity, where you could have proppant settling in the wellbore and a potential screenout risk. And secondly, with a lower velocity into each frac, right? If you have more clusters per stage with that longer stage length, then the velocity of the fluid into any given fracture is lower. which can correspond to a shorter propped length or propped length in the fracture. So conceptually, we know why there's an upper bound, and we also have the incentive to avoid a lower bound. Returning to our philosophy of sensitivity analysis, our golden rule is we modify only one parameter at a time. What I want to present or talk through are some of the considerations on things that you would want to normalize as you move from one sensitivity to the next. So if we're changing stage length, what are the things that we need to focus on to normalize? I'm going to talk through mesh resolution, cluster spacing, pump schedule, perforation friction. So most of these are pretty intuitive once you think about them, but if you don't think about them, they can result in gotchas. And then finally here on the right-hand side, I added a caveat, which is that given the constraints in the field and how you might actually complete these wells, we acknowledge that you're not going to set up sensitivities, or you're not going to be able to implement well designs where stage length is perfect increments of the mesh resolution so that you can keep that the same, right? However, in your first run of sensitivities, we really urge you to do that in a way that you're able to normalize on mesh resolution and cluster spacing and pump schedule, even if that's not actually what you'll implement, because that way you can disseminate and decipher what the impact of that variable is from the other variables. And then go back and run a couple other sensitivities on designs that could actually be implemented in the field. So as an example, if I were doing a sensitivity on stage length, I want my mesh resolution to be the same for each sensitivity, and I want my cluster spacing to also be the same. So if my base case was this 180-foot long stage with 6 clusters, you can see that I have 12 elements in the wellbore direction for those 6 clusters. And so I want to maintain that same resolution. You can see that the grid cells are the same across all 3 of these. And my cluster spacing is the same. And so this may be my initial sensitivity run, where I look at 6 clusters at 180 feet or 240 feet at 8 clusters and 300 feet at 10 clusters. But in all of these, my cluster spacing is 30 feet and my mesh resolution is the same, right? 15-foot mesh resolution along wellbore strike. And what this allows me to do is to specifically look at the impact that stage length has on performance. And then when I go back, maybe I'd say, well, the actual implementation would be a 250-foot stage. And so I can run that simulation and assess the impact at whatever cluster spacing, but I do so already with the knowledge of what % of that impact is a result of the cluster length or the stage length rather than some other parameter like cluster spacing. So then the others are pretty intuitive, right? You want to keep the cluster spacing the same, even though you may change it in the future. You want to keep your pump schedule the same, even though you may change it in the future. You want to keep the total proppant the same, even though you may change it in the future. And that way you are normalizing. And maybe to add clarity here, because I forgot to add a slide on that particular, the total proppant, what I mean here is total proppant per lateral foot, right? And so if I want to keep the injection rate the same, because that's going to impact things like limited entry, then I want to just increase the duration of my pump schedule proportional to the length difference. So if I'm going from 180 to 240, right, I have increased my stage length by 33%. And so then I would extend the duration of each of those injection ramps by 33%, such that I have the same total pounds of proppant and total fluid per lateral foot of my model. And then we talked about limited entry 2 weeks ago. The same would apply for a stage spacing simulation or stage length sensitivity analysis. So this perforation friction or limited entry is this concept of back pressure. So when I'm forcing fluid through an orifice, there is a pressure drop that occurs as these streamlines converge and then diverge as they exit the orifice. And that degree of pressure drop is proportional to the flow rate and then inversely proportional to the number of holes, the diameter of those holes, and the coefficient of discharge. And why we care about normalizing this is that it will impact things like perforation efficiency. So the more back pressure you have, or the higher delta P that you have, the more the fluid will evenly distribute across your various clusters and perforations. And so when we're running our sensitivity analysis, we want to normalize that back pressure so that we're not seeing an impact of, say, increasing or decreasing that perf friction. An example of this would be if I come back to this example, and here I have added 33% more clusters, right? Originally I had 6 clusters, and I've added 2 clusters to have 8. If I kept the number of perforations per cluster the same, now I have far more holes in my pipe in a given stage, and so my perf friction is now lower, which that alone gives me a propensity to lower perforation efficiency. And so if I didn't normalize, I may find that this 240-foot stage underperforms on a per foot basis the 180-foot stage. But that's not entirely the effect of stage length. It may be more an effect of perforation efficiency. And so that's why it's really important to consider normalizing these things as we set up the sensitivity analyses. So the example here is if I started with a base case that had 8 clusters per stage, so maybe that 180 or 280? 240-foot stage, so this case has 8 clusters. Maybe that's my base case with a perforation friction of 800 psi when I actually calculate it. If I then went to the right-hand case, which has 12 clusters per stage, in order to normalize this in the model, I would lower the number of perforations from 4 perfs per cluster to 3 perfs per cluster, and I'd change the hole size to 0.377, and I'd end up with a perforation friction of 800 psi again. And that way I'm avoiding any impact from the perforation friction. Now, you'll come back to me and say, well, I can't actually differentiate between a 0.37-inch hole and a 0.4-inch hole when I'm buying guns. Yes, I acknowledge that. That's why we'll run additional cases afterwards. But again, we want to assess what degree of impact does that stage length by itself have as opposed to these other confounding parameters. So with that, setting up these simulations is pretty simple, right? So if you're using the inline method, you would just use the stage spacing wizard, which is in the wells and perforations panel, and it asks you what is the total length of lateral you want to model and how long are each of your stages. So I would just go in and I would change the stage length, and then I would also commensurately increase the cluster count when I run the wizard. And in doing so, it will space the clusters at the same increment as my base case. And then I'll go back and check the meshing tab and confirm that I have the same element length in each of the directions. And after I do that, I can run my cases and then evaluate various metrics. So as we said last time with cluster spacing, at the end of the day, what we really want is some financial or objective variable versus our independent. So if we look at something like stage length on the x-axis, and then you could plot MPV or rate of return or internal rate of return versus that stage length and pick your optimal point. That's what we want at the end of the day. But the advantage of using this physics-based solution is we can then take that point, our optimal solution, and explain why it is optimal. So what are some of the ideas behind that? Of course, production versus time is a great one to look at, and total propped area that is created. Now, one of the gotchas here is that we are changing stage length between these simulations, and since because we typically only model a handful of stages in a well, you can't just use the built-in features to compare simulations because we need to normalize on lateral length. And so I recommend taking the results into something like Excel or Python, and then you could take total production and divide by the lateral length to get your barrels per foot or MCF per foot that you are producing, and compare directly on that. Similarly with the propped area, if you divide by lateral length, then you can compare like to like. Last time we also talked about RTA. So again, you'd want to normalize this. If you're curious, I can send you an Excel sheet to make RTA plots, and that will allow you to normalize for that lateral length and compare, are we seeing a difference in RTA when we increase stage length? Unless you're screening out, default assumption would be that they should look fairly similar, but sometimes we're surprised by the results. So take a look. I also like to look at pressure distribution in a 3D plot. And as I said at the beginning, that lower velocity per fracture can actually curtail prop length, which would then curtail the depletion length of a fracture. And so if I were comparing something like a 500-foot stage to a 250-foot stage, I very well may see a substantive decrease in the drainage region next to the well, right? Because the velocity just isn't high enough to carry the proppant out farther. So bird's eye view of pressure depletion through time can be very helpful. Another one that's in the Viz tool that I recommend looking at is the superficial velocity. So here, if we look at the wellbore, you can see the color scale here is the velocity of the injection fluid through the wellbore. And so as we go toward the toe of the stage, the heel is over here, we can see that that velocity is decreasing. And there will come a point where the velocity of the slurry is too low to continue carrying proppant. And so if I look at the superficial velocity next to the proppant total volume fraction, I may start to see proppant being deposited in the wellbore. And at the end of the session today, I will open up the 3D viewer, and I ran a test case to see if I couldn't get that to happen. So that can be our little nugget at the end if the simulation has completed. Carrying on. So this is a little bit of a review and also a little bit of a preview of what we talked about 4 or 6 weeks ago, which was well spacing sensitivities. And what we had discussed was this complex geometry problem of if you have a well that is off of one of your cardinal coordinates, how do you shift that well? And we went through the geometry where there's some cosines and some sines and a shift. And ultimately what you're able to do is shift these wells and populate such that you might have 3, 4, 6 wells to assess well spacing and the impact that that has. And I provided a spreadsheet if you want to calculate this. However, what we didn't talk about were some of the features that might be helpful in setting up different well spacing sensitivities. So I'm going to cover 2 of those features that can help. and then we'll look at how we might apply those. Zero permeability cubes would be the first of those features. And we have two different zero permeability cubes. The first type is called a zero permeability outside cube. So you can see in this image down below, what I have done is I've specified a matrix region, and then I have zeroed out the permeability to the top and bottom of this blue region. And where that may be helpful is if I have multiple wells, I could orient that cube the other direction, and I can make it time dependent. So I could have fractures propagate out into this outside region, and then I could turn on the zero permeability cube after fracturing, such that those fractures did not drain from a region that ostensibly another well could be located in. Alternatively, there's this zero permeability inside cube method. And so you can see here, I've placed a cube just to the upper side of my wellbore. And so permeability within this cube is now 0. And so production will not be able to come, or fluids will not be able to flow from within that cube. And again, we'll look at a couple schematics of how I might combine these or use these during a well spacing sensitivity analysis. And then the other feature is the external fractures. So as we talked about earlier, we typically only model a portion of the lateral for computational simplicity. And so one feature that can help is this concept of an external fracture, where we specify a fracture outside of the matrix region. So you can see here are the perforations that I'm going to model. And so my matrix region actually ends right about where my red cursor is. And then I've placed this fracture outside of the matrix region and given it a net pressure, which is also time dependent. And so what happens is I have specified a net pressure of about 500 PSI in this fracture. And so it's stress shadowing those stages that I'm about to model. And then over time, it decays back to a lower net pressure. And I can define that curve shape and how quickly it decays. And in that way, I'm simulating a prior stage having been fractured and then leaking off as I start to fracture the stages in my model. So how can I apply these? Let's say I was doing a spacing sensitivity in a single zone. Well, I could include 3 wells in that zone, and these white checkered wells is where my next wells would logically be. I won't include those in my model, but instead I'll put a zero permeability outside cube around those 3 wells, such that the edge of the cube is halfway in between my modeled well and my non-modeled well. And so you may ask, why not just make my matrix region the size of my zero perm cube? And it's because I expect my hydraulic fracture length to extend beyond that halfway point. And so I want the well to be able to create those fractures that extend out beyond its drainage region. But then I'm going to implement the zero permeability cube such that it cannot drain from the tips of those fractures.
Hey, Garrett,
Yes, sir.
can you do something besides 0? I mean, if you assume maybe you have 80% or 60% outside the cube, can you do that instead of saying 0 permeability?
You could, it would be a little bit more complex. So the zero permeability cube is a direct input, right? So you can specify geometry in the simulator and implement it. There is also general heterogeneity in the simulator. And so you could actually look at geometrically where within your mesh these elements would be. And then you could apply a permeability reduction to those. if it's something you want to do, let me know, and we can help you set that up. And if it turns out to be something kind of routine, then we would maybe put it as a feature inside instead of a zero permeability cube, it could be a perm modification cube.
Okay. Can you also do something? You also do something with depletion pressure out in that outside the cube, don't you? For those other wells, do you do anything with a reduced reservoir pressure out there?
We do not. And
Hey,
again,
Garrett, I don't think that's totally true. This is Dave Ratcliffe. Hey, Dave.
Hi, Dave.
So yes, if you had wanted to, say you set all 5 of those wells up, you could actually set the wells up to deplete that zone, but then that kind of goes against using the zero perm cube.
Right.
So you can't put it in there depleted. You'd have to frack the well, deplete it as a normal well, Dave.
Okay.
Yeah, that's
Just
right.
be a bigger model is what we'd be getting at is all I'm getting at. So yeah, you can create that depleted zone, but you have to you can't input it as depleted already.
Okay. Thanks.
And there's several options that you could do that, right? So what Dave Ratcliffe was just describing was, you would increase your model domain where these actually become black, so they're included in the model. You could still, if you weren't worried about history matching those wells, and you're still just trying to history match or assess your sensitivities on these 3 wells in the center, but you wanted to account for depletion, the way I would do that is with pre-existing fractures, which is different from an external fracture, right? So the pre-existing fracture is where you can specify a geometry of a fracture in situ. And so you could do that on these 2 edge wells and then drain from those fractures and deplete the reservoir to whatever degree that you had intended to deplete. And that would be computationally more efficient because you're not actually simulating the propagation of fractures. And it's a little bit less accurate. You're not capturing maybe the stress shadowing and sequencing of fracturing operations, but that would be the way I would encourage you to incorporate that depletion offside if you think that's going to have a big impact.
Okay, thanks.
So then we can step up the complexity. So with, in the Permian or other areas, you might have multiple benches with multiple wells and thinking about how to set up a well spacing sensitivity. Well, the simple and approximated way to maybe apply this zero permeability region would be to take those 3 center wells in each zone and kind of draw that cube approximately around those. So you can see I've kind of drawn it halfway over here and halfway over there, but this edge well is a little bit closer and this one's a little bit farther away. And so it does introduce a little bit of asymmetry here, but it would be an approximate method. And at the end of the day, these are all approximate. And what I forgot to mention is I would generally assess this center well, right? So my assumption is that this pattern continues on left and right. And so the depletion effects are actually being and stress effects are being accounted for by these 2 outside wells. And then I'm assessing production potential on the center well in each zone. If I want to get a little bit more complicated, I can actually do a larger zero perm outside cube and then place smaller zero perm inside cubes in each zone. And that way, each of these edge wells is symmetric to its zero or no flow boundary. And again, it's a little bit imperfect because there is likely frac growth happening between zones, right? And so if you just make that zero perm inside cube within a single zone, in reality, maybe this well would be draining a little bit from there. And so there's always approximations that have to happen. But again, we want to do as much realism as possible or account for it. And then I would assess in terms of MPV analysis, I'd ratio back to a well and then extrapolate that to what that would be if I continued that pattern across an entire section. And I'd do so on this center well. Those are just a couple comments on well spacing as I thought about that after our last office hours. There's no exactly wrong, exactly right way to do this. So feel free to contact us if you have questions or want input on how you think might be best to set up a more complex model. Okay, well with that, I promised I was running this sensitivity. I don't think it's run long enough, so we can open it up and take a look, but I will ask Tristan to email out a picture of the proppant settling in the wellbore because I'm not sure it will have happened quite yet. We'll take a look though. Okay, so there's my pressure plot. Here's the pressure in the wellbore. Let's go ahead and stretch a little bit. I've gone inside my simulation. So we can turn off the matrix, turn on my perforations. And what I did to set this up is I made a long stage length with, I think I have 20 or 25 perforations, and wanted to see whether or not we could see proppant settling in the wellbore. So I'll take a look at proppant volume fraction. Might need to reduce my stretch. And so we do start to see this happening here toward the toe. So again, color scale here is the proppant volume fraction. And so we can see that over here toward the heel of the wellbore is blue. And then, actually here, let's do this as well. Let's plot that superficial velocity that I previewed. So here toward the heel, we see that superficial velocity is maybe in the 50 to 60 feet per second. And that proppant volume fraction is effectively zero. Now it's not zero because we're pumping proppant into these fractures. As you can see, there is proppant entering into the fractures, and the aperture, of course, of a fracture is very small, which is why that volume fraction increases. But in the wellbore itself, we're probably down at something less than 5% volume fraction. Now, as I scroll toward the toe, you can see my superficial velocity is falling. Now I'm down to maybe this 37 feet per second. And imperceptibly, you can see I'm getting a little bit greener. And as I continue along here, now you can see that wellbore has turned green. So now I'm up at 5% or more. And my superficial velocity is down to about 18 feet per second. If I continue, oh, there's the toe. So you can see here, and we could zoom in more just to see. I'm gonna call that right about 4% is what the color is in my wellbore. And so proppant is starting to deposit. And we're still at the beginning of the stage. You can see this is only 1 hour in. We are probably, I think I have it set up for like a 3-hour injection schedule. And what's going to happen is that once this proppant is deposited in a bed along the base of the wellbore, it's not going to remobilize. It's not going to suddenly then go into a fracture. And so toward the end of the stage, we may actually screen out in the toe because of this proppant accumulation. So I'll mess around with it tonight, and I'll try to send out an update when Tristan sends out the video recording next week. Okay, so there's a question on the setup of external fractures for like a multiple well development. Maybe I will go back to my handy dandy drawing mechanism. So the question is, oh, I'm not sure I'm going to be able to draw in 3 dimensions here. This is always dangerous. But if we had a multi-well kind of stacked development, what is the best practice for using external fractures? And the answer is 1 per well. And even if so maybe backing up, how do we pick what size to use for an external fracture? Well, on the first run, what I do is I often just approximate the size. And you can see these are ellipsoidal. And so I'm going to say, I kind of expect my fracture to be 1,000 feet long and 200 feet high. And so I'll just put those dimensions in, and I'll put the center point 1 cluster spacing away from my toemost cluster. And then I will put in the 1,000 feet and 200 foot height and run a simulation. And if my fracture dimensions in my actual simulation end up being a little bit different, I may adjust my external fracture just slightly to match the average fracture shape of those created in the actual stage that I'm simulating. And I'm going to assign 1 per well, and they may overlap. And what happens is the code can then calculate the impact of overlapping, right? So there's an additive effect if you have multiple fractures where they overlap on the tips. And so the code will handle that, and it'll handle the overlap of external fractures. And that applies to multiple zones as well. So if I had this case, I would likely have 9 external fractures. If I just pop into one of these simulations, we can see how to make these time dependent as well. So the external fracture options are available under wells and perforations. If I come here, you can see I have this well called well demo. And I have 1 external fracture set up. And if I scroll across, you'll see I apply a center coordinate. So this is placed at the toe of my well. So here's my model setup. You can see my matrix region. If I come to toggles, you'll see there's one for external fractures. If I turn that on, sure enough, you can see here's my external fracture. And if I tilt up, you can see it's outside of my matrix region. And if I continue scrolling across, you can see there's 3 inputs that I use: a half length, half height, and then a net pressure. And so that will define how much of a stress shadow is being created by that fracture. And then what you'll see is there's several more options as I continue going. So there's one called closure time and then residual fraction. And so what this does is it says I put in a net pressure of 500 PSI and a closure time of 3 hours and a residual fraction of 0.4. So what the code will do is at time 0, or more precisely, at activation time, and you can see I've set it to 0. At time 0, the net pressure in that external fracture will be 500. And then over the course of 3 hours, the net pressure is going to decrease to a residual fraction of 0.4 times 500, or 200 PSI. And then you'll see there's additional activation times. So if I were, say, to re-pump into that fracture for some reason, I could have it almost blink back and forth. Although most commonly what I'm going to do is just change the activation time. So let's say I had 2 wells. Then I would add a new row, or actually, easier way is I can just duplicate that row. And let's say I'd space these wells 500 feet apart. So I'll just move that fracture by 500 feet. I would also do that to that wellbore. But if I'm zippering back and forth, then maybe my activation time is 3 hours. And so what the code will do is this second external fracture will be have a net pressure of 0, so it won't exist until 3 hours. And then at hour 3, it will have a net pressure of 500 and deplete until, or decrease until hour 8, or I'm sorry, 6. I can't do addition right now. Decrease until hour 6, at which point it'll have a net pressure of 200 psi. And so in that way, you can simulate the zippering order of wells with external fractures as well. Well, I'm not seeing any hands or additional questions coming in. So we may be wrapping up for the season here. Bonus points if anyone else dressed festively in the last 51 minutes since joining.
So now you tell us that that was our goal for the last 51 minutes.
Should have been getting dressed instead of listening to you, huh?
Dude, yes.
And it may have been a counterproductive challenge to have levied to the crowd. Well, with that, I hope everyone has a great holiday wherever you are, and stay safe. We'll look forward to seeing you all in January and continuing this. So as promised, I'm following up with an example of that screenout due to proppant settling in the wellbore. This is that same simulation we took a look at the end of office hours. I'm now just appending it to the presentation. So we see a typical about 2.5 hour pump schedule. In purple here, we have the proppant ramps. In blue, we have the injection rate. And then in orange, we have the wellhead pressure. And so you see that this job is progressing as expected until about this 2.25 hour mark. And then wellhead pressure starts escalating very quickly. What is occurring at that point is that with this extended stage length, the velocity in the wellbore of the injection fluid is slowing down. So if we went to the time step before this, we'd see that the toe velocity is getting very low as all these fractures start propagating. And proppant starts settling in the wellbore. So if we look at this color scale and the proppant total volume fraction, we can see that the wellbore is actually filling with proppant up until the point that it screens out. And that screen out is going to occur somewhere in the 0.4 to 0.6 range. And that's exactly what's occurring here, right where this arrow is pointing, is that enough proppant has accumulated in the wellbore that it actually ends up plugging the rest of flow. So we see flow toward the toe goes to 0. And these fractures on the toe side of the well are no longer being stimulated with the incoming or inbound proppant. As a result, the wellhead pressure starts spiking as we're trying to pump into fewer fractures. And we actually hit the wellhead pressure constraint, which is why you can see that this blue line then dips which is evidencing a localized screen out.